Yeah, everyone, good evening. So welcome to another session R for Epid. So last session, we were on cleaning data and core functions. So we're about to enter the cumulative mass section. So we talked about cleaning pipeline, how to load packages, import our data, clean our column names. We also talked about selecting columns, deduplication, column creation, a lot of things related to cleaning of data and functions for cleaning data. So now I'm going to continue with the cumulative mass. So in this section, we're going to reflect on how to use the sum, the mean, most of these aggregation functions to aggregate our data. So you can see an example here. The sum function is used to aggregate the elements of the vector. We also have the cumulative sum, which is also used to return the cumulative sum at each step. So this is just two types of these aggregator functions. And we also have this is also another code here. So let's copy this and go back to our app. So let me just okay. Okay. So let me open the file we used the last time. Okay. So these were the files we used in last time. So let me just run everything. Okay, Pacman is not installed. Install.packages. So if you follow the last session, you don't just have to run all the scripts we typed in the last session, then just proceed from there. So let me run on. Okay. Okay, so before that does, so let's just look at what we have here. The cumulative mass, where is it? Okay, I think there's somewhere below here. Okay. Okay, so now this is a code that we have in this place. We are going to use it to take the cumulative sum. So calculate the cumulative number of cases per day in an outbreak. So this is going to be a cumulative number of cases per day in an outbreak. So let's copy this. And we hope this has already done. I don't know what the issue is. Okay, it's trying to install packages that are not available. So I take the cumulative sum for the total number of cases. So these are the number of cases we have in a day. So I want to take the cumulative sum, which you can see we have 1, then the second day is 2, 3, so up to 10. So they're asking us to see the epidemic curves for how to plot cumulative incidence with the epic curve. Okay, so I don't know, I'm still having, this should be done by now. Okay, so okay, so this is our code that we have pasted here. So first of all, we talked about our pipe operator. We're going to use our line list. Then we are going to count. So we're going to count the date onset, number of cases. Then we now create a new variable using the mutate function to take the cumulative sum. So if we run this now, we can see what we have. Let's call the cumulative case and see. Cumulative case counts. So this is the cumulative case count. So just you can see it here. So we have other functions, cum sum, cum mean, cum mean, then we have cum min for minimum. This one is for average, cum max, cum many, cum odd. So these are the various cumulative mass functions that we can use. And also using base R also, we can also use base R. We have the $sign, which is used to accessing the column in a data frame. So we can use this $sign to access columns in a data frame. And we also have the assignment operator to define new values, which I've been using all this while. You can see the assignment operator. You can also use the equals to, but it's always a good practice to use the assignment. You can leave the equals to for arguments inside a function. So this is an example now. We are creating a new column now, just using base R. So this just is easiest way of creating a bulk column, no package. So we're going to use the BMI. We have the BMI column inside the line list data frame, or using the $sign to access the BMI data frame and the BMI column. Then also use the $sign to access the weight kg. Then use the $sign to access height in centimeters, so by 100. So we just run this and okay, I think it's telling me of some issue. What's the problem? Okay, I think there's an extra. Okay, I think there's an extra bracket there. Okay, so if I check the line list now, let's say line list. So you can see if you check here, we're going to have the BMI. So this is the BMI that we just created. So this is the BMI we just created, as you can see it's here. So that's how we can use base R. We can also add to pipe chain. So we can add a new column is added to the pipe chain and some classes are converted. So this is our pipe chain now. I already explained our pipe chain is just a chain of operations using the pipe operator. So this is our pipe chain. We can have janitors. This is what we did earlier on last session. We cleaned the names. We also renamed some columns. We selected a column. We removed removed duplications on columns. We also mutate to created a new column using BMI. So this time around, this is the same thing we did earlier on, but with base R. Then also have mutate convert class to columns. So we can just run this and we have what we are trying to have. So there are a few scenarios also where you need to recode columns. Okay. I think some columns doesn't exist. I don't know. To run everything again. Okay. So there are a few scenarios where you need to recode / change the values. So to edit one specific value in your data, which is in incorrect year or format. Then to also reconcile, I don't know, it's telling me some issues. I don't know what the problem is. Then to reconcile values not spelled the same, to create a new column of categorical values and to create a new column of numeric categories. So these are the various ways which you can use to recode values. Or scenarios, I mean, that we can use to recode values. So specific value, we want to change a value manually, you can use the recode function within the mutate. So this is an example now. I want to fix incorrect value. We're going to replace this with this. So we're just going to copy this and run. Let's just paste this here and run it. And we have already fixed this particular issue now. So we are just going to use the recode function inside the mutate function. So this is also another example, recording multiple values within one column. So these are multiple values we are trying to record within a single value, within a single column. So here we have, in the line list, where we have column, we want to clean the line list values in the hospital column. So we are going to use this function table. So let me just copy it and run it here. We'll have a view of it. So you can see this is their column, hospital column, and we are trying to clean it. Use NA. So they said that the values in the columns must be clean. There are several different misspelling and missing values. So this now we are using a code. This is a multiple recode, as you can see. Because this is, we are fixing a lot of these values. So using the recode function, using the recode function inside the hospital variable. So now I already fixed this from you can see this military hospital to military hospital. We have fixed all this spelling using that particular recode function. So this is how that actually goes. So now we see the spellings in the hospital column have been corrected and consolidated. So let me just copy this also in the paste. This also, so let's check it now. You can see it's now corrected. So now here's a tip now. The number of spaces before and after an equal sign does not matter. So make your code easier to read by aligning the equals to for all or most rows. Also consider a hashed comment row to clarify for future readers which side is old and which side is new. So try to clarify. So like something like this now, old is equals to new. So this is good. So that in case someone is trying to read your code, the person will understand what's going on. Sometimes a blank character value exists in a data set, not recognized as R's value for missing. So you can reference this value with two quotation marks with no space in between. So a blank character value exists in a data set, not recognized as R value for missing. So you can also reference this value with two quotation marks with no. So anytime you have blank values, you can reference them with two quotation marks to represent missing values. Okay, now, so for biologic, we demonstrate how to decode values in a column using logic and conditions. So you can see we use the replace, if else for simple logic, and this you can also replace value or recode values in a column using these particular logics and conditions. So you can use the case when for more complex logic. So this is the first example on the replace. So now you can see you want to use the replace now to change just one value in a row using a unique row identifier. So below, the gender is changed to female in the row where column case ID is to 195. So this column case ID now, we have a case ID now. We're interested in changing that particular case ID, the gender of the case ID from male to female. And that case ID is 2195. So this is we are going to be using the replace function inside the mutate function. So first of all, we change our data set and use the mutate. So we can now see that gender is now equals to replace the gender. Then we are going using the replace. The first argument we are giving the column, they will now say the case ID is 2195 and you should replace it as female. So if we should run this now, we are going to see that that particular case value 2195. So let's say I'm saying line lists, then the filter can now see gender is equals, okay, let me just say case ID. Since case ID is equals to 2195. So, okay, I don't know. Let me see. What's happening? Let me check this. Okay. I don't know. Let me see the case ID. So I don't know, since we don't have a case ID of 2195 in the data sets, but you can just do the similar for any other ID you have. Okay, so the equivalent command using base R syntax. So using base R syntax is just the equivalent command. You just paste this and you access your column using the $sign, and you can see the line list case ID is equal to 2195 and it's female. So this is it. So we also have the if else and if else function. Another tool for simple logic is if else and its partner is if else. So however, in most cases for recording, it's more clear to use case when. So if else commands are simplified versions of an if and else programming statement. And so the general syntax is this. So we can use the if else and this particular these two if else functions, can use them to also recode values. Like now in this particular example now, so we have a value in a given row set to none. If the row's value is in column source is not missing, and the value in source is missing, then the value in source none is set to unknown. So what this is just trying to tell us, if you look at this code now, this command, I'm just going to say mutate. So source known, if else, that is if the source is known, that's if we have the value of known. Okay, now this is n source. It's trying to tell us that if a source is not a missing value, then set it as known, else we should set it as unknown. So if a source now is not a missing value, set it as known, or you should set it as unknown. So this if else is also a special case from dplyr that handle date. So this if else is mostly for date. So if the true value is a date, then the first value must also qualify a date, hence using the special value NA instead of just NA. So this is also another if else. And just replace this now. So it's saying mutate date death. So if else outcome, if the outcome is death, then the date should be the outcome. Then we should have date outcome. So if outcome is equal to death, then we should have the date outcome. Else is going to be the NA rate. So this date outcome is going to be the date that the person actually died. Else is going to, you are going to leave it as a NA instead of NA real, instead of NA. So NA real qualifies mostly for date values. So now, but when you have complex conditions, what will you do? Are you going to be using a nested if else? Well, it's not advisable. So this is where we have to use the case when. So you can also use the switch from base R. It's just like a similarity between, there's just similar to the case when function for the dplyr. So now this is where we use a complex logic. Now you can see if in this example now, we are trying to so this is the example we have now. We are trying to use the case when. So in the case when now, we are going to use the mutate function. We are going to use it inside the mutate function. So whether you're creating a new column or you are just replacing a column. So first of all, we say if the age units is equals to yes, then you should represent it, replace as age instead of yes. So inside this particular age, yes. So if the age unit is in years, they represent it by age. So this age that you are seeing is not actually a value. It's the value for that respective column of age. So we have a column called age. So it's going to take that value and replace it. If the age unit is in years, you should replace it as what? Age. You should take that particular age value because we are creating a new column now called age in years. Earlier on, the age column was mixed. So we have in years, we have in months, we have different types of units that were used for the age column. So now we are trying to create a new column called age years. So if the age unit is in year, which is in years, then you should just put that same value. You should not perform any action on it. But if the age unit is in months, then you should divide that particular age by 12 to represent it in years. And if it's an NA, then if the age unit is in NA, then you should just give us the value of that particular age, which is actually NA. So this is how a complex if statement works, which is using the case when function. So when you use the case when function, you are going to get this. So this is just an example. I don't know why it's not running what the issue is. Or this. But at least we understand the points and we understand how the case when actually works. So we have the line list in this place. So the line list imitates case status. Okay, so this was another example of the case when. So you can see now if case status, we're creating a new column called case status, and if CT blood is less than 20, then you should put a value of confirmed inside this particular new column. Or if the source is missing, is not missing, and it is fever, you should put the value as yes, then suspect, you can see it, then true to investigate. So true is used to follow any other value that wasn't actually covered. So we use true, then true now to investigate. Any other condition that was not covered here, then it's going to be replaced with to investigate. So we have a warning here that values on the right side must all be the same class, either numeric, character, date, logical. To assign missing values, you may need to use special variations, such as any character, NA real for numeric, or POSIX, use NA real for character, use any character, and as .date NA. So we can have more details on working with date. So the next is missing values. So we have special functions for handling missing values in the concept of data cleaning. We have the SNA function and also have the replace NA. So you use the replace NA if you actually want to replace your missing value with a value. So for example, now inside this, we are going to just be replacing. So you can see we are replacing missing values inside the column hospital with the value of missing. So we have SCT explicit NA. So this is a function from the forecast package that handles columns of factors SCT explicit NA. So we have first, second, and third order to set the order that velocity hospitals appears in tables and plots. So this is a function from the forecast package that handles columns of class factor. So if your data are class factor and you try to convert NA to missing by using replace NA, you get this error invalid factor level. So that means it's not going to, it's not easy to replace factors with, it's not easy to use the replace NA to replace factor variables. So you need to use a special function called FCT explicit NA. So we're going to use the forecast library, which we could have already installed earlier on. So use the SCT explicit NA on the hospital. So it's going to convert a column to so if we can solve this issue using the forecast function SCT explicit NA, which converts a column to class factor and converts NA values to the class character. So another slower alternative is use the add factor level using FCT expand and then convert the missing values. So to convert a specific value to NA, we use dplyers NA if the command below. So we can use this to convert a specific value to NA. So we can know that NA if cannot be used for logic criteria. Use replace or case when for this. So we can also use the NA if command below. So you want to convert a specific value NA, use dplyr NA if the command below performs the opposite operation of replace NA. So in the example below, any value of missing the column hospital are converted to NA. So also have the NA if cannot be used for logic criteria, use the replace or case when for this. So we have cleaning dictionary. We use the R package match picker and its function match DF to clean a data frame with a cleaning dictionary. So create a cleaning dictionary with 3 columns. A from column, that's the incorrect value. 2 columns. So if you have you want to replace some values, you have to have a clean dictionary using the matchmaker library. So you have to create a data frame with from, to, and we have a column specifying the column for the changes to be applied. So you want to replace a lot of values, you have to use a cleaning dictionary. So let's say from a particular column to a particular, from a value to a particular value, then you now create a column. Are you applying it global or applying it to all outcomes? So what are you trying to replace? Is it global or is to all the outcomes? So import the dictionary file into R. So this is we are going to import this particular dictionary file into R. Then once we import it into R, so this, then we can now import it. Then we now use this particular matchmaker library. We now say dictionary, we are allowed to access that particular clean dictionary from, we say that's from which columns to which column by which column. So where are we replacing that particular value? Is it globally or present to a particular specific column? So we can now use that to also clean our data assets. So this is all what we have already done so far. So I think we can just run this. This is all what I've done on the line list column. I don't know. I think the particular column is not here, so that's why maybe we're having errors. So we have what we call numeric categories. So here we describe some special approaches for creating categories from numerical columns Common example include age categories, group of lab values, and we're going to talk about the age categories from the EpiKits package for creating age categories. We have the cut from the star, we have the kiss when, also have contact breaks with contact and end time. So I want to create an age category column using the AGS column class, and which is numeric. So let's just take this. Node. Then first example, the distribution of the data to make appropriate cutoff points. So let's example, okay, I don't know what was happening. I thought we have a AGS. Okay, I think this is where the issues. We have to create this. It's telling us column X28 does not exist. I don't know why the problem. Okay, let me run on and see. The same column X28 does not exist. So let me try and remove this and see. Let me run it again. I think this should work now. Yeah. So this is the distribution of the line in this age in years. So this is the distribution. This is how it looks like. And summary. You can get a summary of it. So this is a summary for it. And sometimes we have a caution here telling us that sometimes numeric variables will import as class character. So this occurs if there are non-numeric characters in some of the values. So for example, if I have an entry of 2 months for age, or depending on your R local settings, if the comma is using the decimal place, then e.g. 4,5 to mean 4.5 years. So also we have age categories. You can use the age categories function in the EpiKits package to easily categorize and label numeric columns. Note this function can only be applied to non-age numeric variables too. As a bonus, the output column is automatically an ordered factor. So this is the EpiKits package. We can use it to create our columns in years. So we can create our columns using the EpiKits package in years. That's our age in years. We can use it to create a category for these particular columns. So the break values you specify are by default the lower bounds. So that is they are included in the higher group. So the groups are open. So we're more or less just breaking the particular age in years into categories. So these are the breakers we have. We have 0, 5, 10, 15, 20, 30, 40, 50, 60, and 70. So you can see this is the table already have already. We have it's 0 to 4. We have 1,227, 5 to 9, 1,223, and so on and so forth. You can see for NA we have 107. So this is more or less instead of using the case when function to categorize the age, you can just use this particular age categories function to break the age and can specify the breakers inside this particular breakers argument for the age categories function. So this breakers is more or less like where the age is going to start from at the next category. So you can also include upper ends for the same categories. So you can also include an upper end for the same categories, as you can see in this place also. So this is also similar to what we just did earlier on. So you can also adjust the labels, how they are displayed with the separator arguments. So the default separator is actually an hyphen. So you want to use a column, you can actually use a column. So you can just have the top numbers are handled using the ceiling arguments, and also set an upper cutoff ceiling or upper cutoff sets using the ceiling is equal to true arguments. So in this use, the highest break value provided is in ceiling, and the category XS plus is not created. So any values above highest break value or upper is defined or categorized as NE. So below is an example where we're using ceiling is equal to true, so that there is no category of XS plus values, and values above 70 are assigned as NE. So also run this now and see, we can see that using ceiling is equal to true now. So values above 70 are applied as NE. So we have set by setting ceiling into true, the ceiling argument as true. We have already, it means that any value above this particular last breaker 70 is going to be replaced as NE. So we can also use instead of breakers arguments, we can also provide options for the lower equals to argument, the upper equals to argument, and the by equals to argument. So this is another example of the line lists. For the line list data set, that's where we're going to be using. So this time around, we're not using the breakers argument, we're using the lower, the upper, and the by argument. So we can see that we still have similar values to what we have. So upper is 0, lower is 0, upper is 100, by is 10. Well, see, this seems to be a little bit more easier than what we said earlier on. So here you can just specify the amount of the class width inside your particular grouping. So we also have the cut argument. Hi everyone. So the last session, we are still on our cleaning data and core functions, and we actually looked at a very lot of functions for grouping age groups, for handling age groups, for reshaping. So the next function I'm going to be talking about is a cut function. So the cut function is base R alternative to age categories. You can use it to also create the categories. But also they also explain the reason why the age categories is better to use the age categories. So because you don't need to install / load another package. That is reason why you might use cut sometimes is that you don't need to install or load another package. You can also specify whether groups are open / or closed on the right or left. You can also provide accurate labels for yourself, and if you want 0 included in the lowest group, you must specify this. So the basic syntax within cut is to first provide the numeric column to be cut, that is age, years, and the breaks argument, which is also a numeric vector that is using the concatenate function of breakpoints. So using cut, the resulting column is an ordered factor. So by default, the categorization occurs so that the right / upper side is open and inclusive, and the left lower side is closed or exclusive. So this is the opposite behavior from the age categories function. So the default labels use the notation AB. So this is lower bound and this is upper bound, which means A is not included. So in this lower bound, A is not included, but B is included in the upper bound. So reverse this behavior by providing the right is equals to true arguments. So thus by default, 0 values are excluded from the lowest group and categorized as missing, and 0 values could be infants coded as age 0. So one has to be very careful. So to change this, add the argument include dot lowest is equals to true, so that any 0 values will be included in the lowest group. So the automatically by the generated label for the lowest category will then be this upper bound, lower bound A and upper bound B. So notice that if you include dot lowest is equals to true argument and right is equals to true, then the extreme inclusion will now apply to the highest breakpoint value and category, not the lowest. So you can provide a vector of customized labels using the labels argument as they are manually written, and one has to also be careful to ensure that they are accurate. So this is an application of the cut. So this time around you can see mutate age category is equals to cut. So first of all, we get the column that we're trying to categorize, then breaks 0, 5, 10, 15, 20, 30, 50, 70, and 100, and include the lowest is equal to true. So that means 0 is going to be included inside the age category. So when we run this now, age years not found, so we need to run the whole. Let's run all and see. So let's run the whole script, see what the issue is. Okay, let's just run below from here. Let's run all cells below. I don't know. I'm still having issue. So this is it. So you can see we're having the same thing we have here. So this is it. So include, so we have NA belonging to here, we have 70 to 100. So you can see in this place we have 50 and 70. This is the category. So this one, 50 and 70 are not actually included here. 30, 20, 15, 10, 5. But the lowest was actually included, which is 0. But for the rest, their lower bounds are not included, as you can see it in this play output. So we'll tell us to check your work, verify that each age value was assigned to the correct category by cross-tabulating the numeric and category columns. And examine the assignment of bounded values, that is 15 if neighboring categories are 10 to 15 and 16 to 20. So these are a table of numeric values, which is line list AGS, and we have category, which is line list age category. So, and also we should put, that is for, I try to do a cross tabulation now of the numeric and category columns. So because we created just a category columns now using the age. So let's see. So you can see now the same result also. So we're trying to make sure that each value was assigned to the correct category, each category. So you can see 0, they're all assigned to the correct category. Then we have 1 also. We have 1, all of them assigned to the correct category. When it comes to 6 and 10, they're all assigned to the right category. So this include lowest is equal to true is going to include 0. So once 0 is included as the lower bound. So for the rest now, if 5 is already included here, then 5 doesn't need to be included in the other one. So that is why you see we are doing it like this. So quantile break. So in common understanding, quantiles or percentiles typically refer to a value below which a proportion of values fall. For example, the 95th percentile of ages is line list. In line list will be the age below which 95% of the age fall. So quantiles or percentiles refer to a value in which a proportion of values fall. So for example, if you say 95th percentile of ages in line list data, so it will be the age below the 95% of the age fall. So when I talk of 95th percentile, we're talking of the ages below the 95 group. So however, in common speech, quartiles and deciles can also refer to the groups of data as equally divided into 4 or 10 groups. So notice there will be one more point than group. So to get quantile breakpoints, you can use quantile from the stats package from base R. You provide a numeric vector, that is a column in the data set, and vector of numeric probability values ranging from 0 to 1. And the breakpoints are returned at the numeric vector. You explore the details of the statistical methodologies by entering quantile. So if your input numeric vector has any missing values, it's best to set na.rm as true. That is inside the function, and set names is equal to false to get an unnamed numeric vector. So this is it. So I'm trying to get the quantile of the last list AGS. This is now in percentile. So that's why I'm seeing it in percentile. It was actually in quartile. You're going to put it in a quartile format, but we're using a percentile format. So paste this here and run this. So you can see we have 0, 6, 13, 23, 33, and 41. So you can use the results of quantile as breakpoints in 8 categories or cuts. So below, we create a new column, deck size, using cuts. Now this time around, we are trying to create a new column now called deck size using the cuts, where the breaks are defined using quantiles on AGS. So now, look at this example now. First of all, we use the mutate to create a new column. So in deck size now is equals to cuts AGS, and the breaks now is going to be quantile. So we're going to use this quantile as the breaks, which is AGS. So probability is equal to sequential 0,1 by 0.1. So we're trying to give we are going to use a decile in this particular case. So this decile is into 10 parts, equal parts, dividing the data set into 10 parts. So, and when we run this now, you can see that this janitor has converted it into a table now. You can see what we are, you can see the things that we are seeing in this place currently. So you can see what we are seeing, valid percent. You can also see the percentage. So evenly sized. You can see also the valid percent. These are also the percentage of NA. So the valid percent are those that doesn't contain any values. So these are we can use quantile to apply on our cuts function. So you can use the cuts. You can also use the 8 categories, any of them, depending on your particular choice. So we have evenly sized groups. Another tool to make numeric groups is the dplyr function entile, which attempts to break data into evenly sized groups. So, but must be aware that unlike with quantile, so one must be aware that unlike the which attempts to break your data, so another tool to make numeric groups is the dplyr function entile, which attempts to break your data into n evenly sized groups. But one must be aware that unlike quantile, the same value could appear in more than one group. So provide a numeric vector and then the number of groups. So the value in the new column created is just group numbers, not the range of value themselves, as when you are using the cut function. So evenly sized group now this time around. So quantile does, unlike quantile, which the same value could appear in more than one group. So provide the numeric vector and then number of groups. So this time around it's going to be evenly sized groups. So let me see. So you can see we're having warning. There are two warnings in summary. The first one is that the argument minimum is equals to min, ags na.rm is equals to true, and in group 11 even groups is equals to missing. So caused by warning in the minimum. So no non-missing arguments to minimum, returning infinity, and run dplyr, last dplyr to see the one remaining warning. So combine and print. Let's combine and print now and see. This is the result of even groups trying to do. So the results, this is the results of the even groups that I see we are trying to split 1 to 10, then NA. This is the even groups that we are trying to do. 6, 4, 5, 1, 50, 6, 50, 6, 50. So percentage, the value percentage, the minimum, and this is the maximum. So you can also use case when dplyr for to create categories from a numeric column, but it's easier to use each category from epicate or cut because this will create an ordered factor automatically. If using case when, please review the proper use as described earlier in the recode value sections of this page. Also, one should be aware that all right-hand side values must be of the same class. Thus, if you want NA on the right side, you either write missing or use the special NA value, NA character. So this is just a combination of all what I've been doing so far. Okay, I think there should be an issue here. Column can't select column X28. I think we might need to remove this, it's giving us issue. We need to remove this, so let's run and see what's. Okay, I think we have run it now. Okay, so now add rows one by one. Adding rows one by one manually is tedious but can be done with add rows. So you can add rows into your data frame. You want to add an observation, so using this particular add row function. So just paste, let's paste this code, and you can see the row number, you can see the case ID, ABC, the generation, which is 4, infection dates as date, and before, which is 2. So when you run this now, so when you should run this, okay, infection dates in, can't find column infection dates. Okay, it's telling us that it can't find the column infection dates, so I don't know. Maybe I should just remove it. So let's just run it just as an example. So if you should run this now and check for this particular row, so let's check for this row and see. I say line list filter row number is equals to 666. So okay, it's supposed to be this row number, I think. Now let me just say case ID. Case ID is equals to ABC. So this is it. So you can see that date. Okay, it's actually date infection, not infection date. So that's it. So this is our row that we just added now. So you can use the dot before and dot after to specify the placement of the row you want to add. that before is equals to 3, which will put the new row before the current stored row. So the default behavior is to add the row to the end. Columns not specified will be left empty. The new row number may look strange, but the row numbers in the existing rows have changed. So if using the command twice, examine/test your insertion carefully. So in case you provide, if a class you provide is off, you will see an error like this. So bind rows. So bind rows to combine data sets together by binding the rows of one data frame to the bottom of another data frame. You can use the bind rows command, and which you can check in journey data. Also have filter rows. A typical cleaning step after you have cleaned the columns and recorded values is to filter the data frames for specific rows using the dplyr verb filter. Within filter, specify the logic that must be true for a row in the data set to be kept. Below we show how to filter rows based on simple and complex logical conditions. So we have simple filter. The simple example defines the data frame line list as itself. I don't filter the rows to meet a logical condition. Only the rows where the logical statement within the parentheses evaluates to true are kept. So in this example, the logical statement is gender, which is equals to false, which is asking whether the value in the column gender is equals to false. Equals to female, I mean. So before the filter is applied, the number of rows in line list is n row line list. So this is just a simple filter to check, keep only rows where gender. This is how to just simple filter. I want to filter missing values, to use the drop NA, we drop rows with missing values. And also to filter by row number. If the data frame or table, each row usually have a row number. So you can filter by row number, that's using the row number function. And also, or you can see row number is in this if it's actually some range of columns, or you can just use head to just filter that particular row number. That is either first n or n rows or last n rows, or to just show a particular number of rows. So this is it. I also have complex filter, which you can use this particular command in and the or, the exclamation mark. These are used for complex filtering. So now let's examine this data. Let's examine our data. So this is our data, as you can see it now. The data, this is the distribution of our line list date onset. So how filters handle missing numeric values? Can we just filter by date onset to rows after June 2013? So caution, applying the code filter date onset greater than as dot date 2013 0601 we remove any rows in the later epidemic with a missing value of onset. Filtering to greater than or less than a date or number can remove any rows with missing values NA. This is because NA is treated as infinitely large and small. So now we also design the filter, examine a cross tabulation to make sure we exclude only the correct rows. So hospital is also line list, hospital, rubric date, year, line list, date, onset, use NA always. So what other criteria can we filter on to remove the first outbreak in 2012 and 2013 from the data set? So we see that the first epidemic in 2012 and 2013 occurred at hospital A, hospital B, and that were also 10 cases at Port Hospital. You can see this is year onset. So first epidemic occurred in hospital A, hospital B, and that were also 10 cases at Port Hospital. Hospitals A and B did not have cases in the second epidemic, but Port Hospital did. So we want to exclude the N row, that is now line list. We are going to exclude hospital A, hospital in hospital A and hospital B. So this is the code we are going to use to exclude rows with onset 12 and 13, and rows from hospital A and B with missing onsets. And we're not going to exclude this is just telling us to filter hospitals that is not in hospital A and hospital B. So this is just a way of excluding hospital A or hospital B. So let's just copy this code and run it here and paste. So we're trying to exclude hospital A and hospital B now. So N row line list is now 6020. So, and this is our table. Let's draw a table of the hospital. Let's draw a table. So this is the table that you can see now, hospital. So this is the hospital, and this is the year onset for each particular hospital. We have already removed hospital A and hospital B. So now standalone filtering can also be done as a standalone command, not part of a pipe chain like other dplyr verbs. You can use filtering as a standalone command. So This place now filter data from conditions for rows to keep. So let's copy this and paste. So you can also use base R to subset using square brackets, which reflects the rows, columns that you want to retain. So this is also another one. Let's use this. And so for rows that one is trying to retain, okay, send my case ID not found. Okay, let me check our line list and see what's happening. Okay, we have case ID. I don't know why it's saying case ID not found. Maybe. Okay, this is just the way of subsetting a particular, or this way of filtering using base R. So you cannot is.na. So any case ID that is missing is going to remove it, not is.na. So it's going to remove that particular case ID. So I think we're supposed to do like this. This is what we're supposed to do. I think this is what we are supposed to have done. That's why. So I think there's an error here. So let me just check the line list now. Okay, so there's an error there. So I also use $sign to refer to this particular column. So that's why we have an error in this place. Okay, so quickly review records. You can use your view line list. It's going to open on another tab. View. You just run view line lists to get line list in another tab. So this is it. This is our view line list. And there are two examples of viewing specific cells, specific rows, and specific columns. So with dplyr, you can also filter for case ID and select that particular columns you're interested in. And you can also do that with the base R syntax. And also, this is now our data. We're adding it to the pipe chain. So let's add it to the pipe chain and add it to the pipe chain, and let's remove this. Or is this particular place that's giving us issue? I think this is it. Let's remove this. Okay, so let's try and remove this. Then let's run this. So this is our first. So this is our data that we have. We already have our final line list now. So line lists, head line lists. So this is our final line list. Row-wise calculation. So you want to perform a calculation within a row, you can use row-wise from dplyr. So you can use the row-wise to perform a calculation within a row. So you are just interested within a row, you can use row-wise. And mutate norm symptoms equal to sum of this, which is going to be equals to yes. So this is another place where I try to perform calculation row-wise. So what we're going to do now, we're going to apply row-wise calculation, then mutate. We are creating a new variable called norm symptoms. So we're going to sum fever, chills, cough, aches, and vomit. So it's going to sum for each of them. Then it's going to be equals to yes. So because each of these now is going to sum each of them and is equals to yes, then on group, then select fever, chills, cough, aches, vomit, norm symptoms. So if we run this now, you can see what we have now. Norm symptoms is now 2. So 2 have what? Yes. So any of them that is equals to yes is now going to what? Is going to give it value of what? 2. So because this is going to return true. If fever is not equals to yes, it's going to be 0, which is going to be false, which is now actually 0. If cheese also is not equals to yes, it's going to be false. So this I can perform a row-wise calculation to add columns together. So now, as you specify the column to evaluate, you may want to use the tidy select helper function described in select section of this page. You just have to make one adjustment because you are not using them with a dplyr function. So put the column specification criteria. We need dplyr function. See across. This is because see across documentation is designed to work with row-wise. Specifically, for example, the following code. So create new column norm na dates. Define for each row as the number of columns which containing dates for which is.na is evaluated to true. So on group to remove the effects of row-wise for subsequent steps. So let me copy this and let's go here, paste, and So num NA date. So this is it now. We have applied row wise, and this time I perform row wise calculation. We have used mutate NA date. So sum is.NA. So all the NA are creating a new column to sum is.NA that contains dates. Then ungroup, then select. Create a new column defined for each row as the number of columns with the name containing date for which is.NA evaluated to true. That means there is missing data in that particular this thing. We also provide other functions such as maximum to get the latest or most recent dates for each row. So we can just paste this also and apply this. So arrange and sort. So you can use the dplyr function to arrange or sort or order the columns by values. So let's say we want to arrange the hospital by date onset. Now we can just copy this and arrange it by date onset. So it's going to be this. So now we're arranging by date onset. So we're going to be starting from that's date. So this is the date onset. From the ascending, this is in descending order now. This is in descending order. We can also do it in ascending order. By default, it's going to be in ascending order. So we run this now by default. So you can see it's going to be in ascending order. So you can see it. So this is how it looks like. So this is it for this particular whole section. It's more or less just about cleaning your data, which is a very important aspect when working with data when working with data, because some of your data are going to be coming as unclean data, are not going to be coming neat. So you need to apply most of these particular functions, or most of these particular function and techniques we just talked about. So see you in the next section.